Every 60 seconds, users push roughly 500 hours of new video into the system. That is an unrelenting, heavy bandwidth pipeline running 24 hours a day, demanding an infrastructure capable of continuous, massive ingestion without dropping a single frame. This chart maps a global video platform's baseline. 1 billion daily active users generate 5 billion views daily. This reveals a core constraint, the read-to-write ratio. For every 100 users watching, only one uploads. 1% of 5 billion views equals 50 million daily uploads. A standard web application handles millions of text-based database writes easily, but an upload of a 4K video is a massive, long-running, heavy binary transfer. Hitting a system with 50 million of these heavy writes a day will instantly choke the network bandwidth and memory of a traditional architecture. To handle this pressure, engineers must prioritize one non-functional requirement above all else: availability over strong consistency. When a user requests a page, the server must return a successful response immediately, even if the data is slightly out of date. If a creator uploads a video and you refresh your feed, you might not see it immediately. Serving slightly stale feeds is acceptable, but a blank screen is an unacceptable failure. This delay happens because the system relies on eventual consistency. Data is copied across multiple global storage nodes, taking time for a new upload to propagate. By allowing nodes to hold slightly different versions of the truth, the system removes single points of failure. Processing 50 million massive file uploads while serving 5 billion instant latency-sensitive video requests requires a specific architectural approach. The platform must aggressively separate the heavy lifting of moving data from the computing logic of the application servers. Left, the naive path. Uploading massive files directly to the API server exhausts memory, causing a complete compute layer collapse. Right, the optimized solution. The server provides a pre-signed URL. The client uses this token to upload chunks directly to blob storage. By routing the physical media files directly to storage, the application servers avoid handling gigabytes of pass-through traffic. They remain free to process lightweight API requests, execute application logic, and keep the platform online. Once the video is secure in storage, the system must manage its metadata, like the video title, the search tags, the live view count, and the creator's user profile. Because of the 5 billion daily views, this metadata layer experiences extreme read frequency. Today, platforms often use denormalized NoSQL databases to duplicate data and avoid slow, complex queries. But in the early 2000s, YouTube founders launched the platform on a standard relational MySQL database. Relational databases struggle under massive read volumes. To keep up, engineers had to create read-only replicas of the database, and eventually had to shard the data, splitting the database into multiple pieces across different machines. This diagram shows the solution they built to manage that complexity: Vitess. Vitess is a database clustering system that sits exactly between the application servers and the sharded MySQL databases. Vitess intercepts queries from the application layer and automatically routes them to the correct database shard. This abstraction means application servers don't hold the complex logic of how the database is divided. They just ask for data, and Vitess handles retrieval. Returning to the raw video file, the system faces its largest compute bottleneck. A single uploaded file cannot be served to every user. It must be transcoded into 15 to 20 different versions to support everything from 4K smart TVs down to older mobile phones. To accelerate processing, the pipeline models work as a directed acyclic graph, or DAC, flowing tasks in one direction. First, it splits the video into keyframe segments. These segments fan out into isolated parallel streams, processed simultaneously by a massive worker fleet. To understand the scale of this worker fleet, look at the ingestion rate. 50 million uploads a day divides down to roughly 500 new videos entering the encoding queue every single second. If encoding a video takes an average of 1 minute, a naive setup of 500 workers fails immediately. In the first second, 500 videos arrive, occupying all 500 workers. In the second second, 500 more hit an immediate backlog. By the time the first minute finishes, the queue is mathematically impossible to clear. To maintain equilibrium against 500 uploads per second, the system requires an absolute baseline of 30,000 parallel workers running simultaneously to prevent backpressure. By structuring the transcoding pipeline as a directed acyclic graph, the platform breaks a monolithic, hours-long processing task into thousands of tiny, independent jobs. This allows the system to scale compute resources horizontally to match the 50 million upload volume. With the files encoded and stored, the architecture must now serve them to 5 billion users a day. When a viewer clicks play and instantly skips to minute 47, the video begins buffering almost exactly at that timestamp. The browser is not downloading a massive, complete MP4 file to your hard drive, nor is it using live streaming protocols designed for real-time sports broadcasts. Looking at this stylized recreation of a browser's network tab, we see the actual mechanism: adaptive bitrate streaming. The browser executes HTTP range requests via XHR, an API that allows web browsers to make background data transfers, pulling down small blocks of the video over TCP. TCP, or Transmission Control Protocol, is a standard that guarantees data packets are delivered reliably and in the correct order. When you load the page, the client first fetches a primary manifest file. This file acts as a directory, listing all the available resolutions and codecs, and providing the exact URLs for every individual segment of the video. Instead of requesting an entire hour of footage, the player requests distinct 5 to 10 megabyte chunks. It only holds the immediate playback horizon in memory. When you seek to a new timestamp, the player simply calculates which segment that timestamp lives in and requests that specific chunk. Delivering video via chunked HTTP requests over TCP gives the platform the strict packet reliability of a static file download while simulating the real-time playback speed of a live stream. Because the video is segmented, the client-side player can actively monitor your network. It calculates the exact time it takes to download recent chunks to estimate your current available bandwidth. If your internet connection suddenly slows down, the video doesn't freeze to buffer. The player simply checks the manifest file and ensures its next HTTP request asks for a lower resolution segment, dropping from 1080p to 480p on the fly. This map displays how these segments are distributed globally using CDNs, or content delivery networks. A CDN is a geographically distributed group of servers designed to cache content close to end users. When a viewer in Tokyo watches a popular video, they aren't pulling the files from an origin server in California. They are fetching those segments from a local edge server in Tokyo. This drastically reduces the latency for the viewer and prevents millions of requests from hitting the origin database, saving the platform from catastrophic network egress costs. Serving 5 billion requests a day is only possible because the platform does not serve whole videos. It pushes billions of static, independent chunks to the extreme edges of the global network, ready to be fetched on demand. Every step of this architecture relies on breaking heavy burdens into smaller components. Pre-signed URLs bypass API servers by chunking uploads directly to storage. Directed acyclic graphs split processing into thousands of parallel worker nodes, and HTTP chunked delivery slices playback into localized, bite-sized network requests. Designing a system for 50 million heavy writes and 5 billion reads isn't about procuring larger servers. It is about systematically ensuring that data at every stage of its lifecycle is distributed, decoupled, and highly parallel.